Good morning, afternoon, evening, whenever you happen to be watching this class. Today we're going to go over chapter 2.4, which is solutions of linear inequalities. So, get my marker ready. Now, first we need to define linear inequality. A linear inequality, or first degree inequality, in the variable x is an inequality that can be written in the form ax plus b is greater than 0, where a is not equal to 0. The inequality symbol can be greater than or equal to, less than, or less than and equal to. So this can change and be any one of these four, and it'll still be considered an inequality. Now in our first example, we have 3x minus 1/3 is less than or equal to negative 4 plus x. And we want to solve for x. Now what I'm going to do first is move the smaller x, just like I would if I was solving a regular equation. So I'm going to subtract x from both sides. This one will cancel. I'll be left with 2x minus 1/3 is less than or equal to negative 4. Now, I want to get x by itself, so I need to add a third to each side. And I'm going to get 2x is less than or equal to negative 4 plus 1/3. And I do need to simplify that. So I'm going to come over here, find a common denominator. That's going to be 3. Obviously, the second one stays the same, but converting negative 4 to something over 3, I need to do 4 times 3, which is 12, and I have converted this to this fraction here. Now I can add them. So negative 12 over 3 plus 1 over 3 is negative 11 over 3. So I get 2x is less than or equal to negative 11 over 3. Now I still got to get rid of this 2 here. I'm going to divide by it over here as well. And I'm going to get that x is less than or equal to negative 11 over 6. And that is going to be my answer. So as long as x is less than or equal to negative 11 over 6, we are good to go. Now something you're going to see with these as well is we're going to spend a lot of time writing these in interval notation. Now if x is less than or equal to negative 11 over 6, that means the biggest it can be is negative 11 over 6. And it can go down from there infinitely. So it'll go from negative infinity all the way up to negative 11 over 6. Just like that. Make sure your negative infinity is first, your negative 11 over 6 is second. You always have to go from smallest to largest in this interval notation. Now example 2 says for an electronic reading device, the weekly revenue and weekly cost in dollars are given by R of x equals 400x and C of x equals 200x plus 16,000 respectively, where x is the number of units produced and sold. For what level of production will a profit result? Now we got to remember that profit is revenue minus cost. So P of x for our profit here equals R of x minus C of x. So our function is going to look something like this. 400x minus parentheses 200x plus 1600. And we're going to simplify this. And we'll simplify it. 400 minus 200 will be 200x. And then that 1600 is going to be negative because we have to distribute that negative to it. Okay, so this is our profit function here, our P of x function. But what we want to know is when will, or what levels of production will a profit result? So in order to make a profit, we have to make more than $0. Okay, can't make $0. You don't make a profit at $0. You make a profit if you make more than $0. So what we're going to want to do here is say, okay, well that means that I need this equation to be greater than 0. Okay, now I can solve for my x here. So as long as this equation turns out to be greater than 0, I have made a profit, because my profit function needs to be greater than 0. So I will add 1600 here, and add 1600 here. And I get 1600 is less than 200x. I will divide by 200 to get x by itself. And let's see, 1600 divided by 200 equals 80. So as long as x is bigger than 80, we have made a profit. So if I were to write this in interval notation, it would look something like 80, comma, infinity. Okay. Now, there is something that is very important to hit, and something we slightly messed up on example 1. Now, in example 2, we are strictly greater than 80, which is why in our interval notation, we need to write a parentheses. And maybe you caught this in example 1, and if it was an in-person class, you would have raised your hand and corrected me. But in example 1, we wrote a parentheses here as well, and that is incorrect. What I need to write here is a bracket. Why? Because it's okay for it to be equal to, so it needs to be included. And the way we show that is a bracket. So make sure you adjust your notes from example 1. If it's not equal to, doesn't have an equal to little bar right there, we use the parentheses, and we always use the parentheses on the infinity. But if it is equal to or can be equal to, we need to put a bracket there. So please be careful of that. It's an easy thing to mess up on. Now, we also deal in some double inequalities. So an example of a double inequality is 0.479 is less than or equal to h is less than or equal to 1.00. Now, a student has taken 4 tests with grades 90, 88, 93, and 85. If 5 tests count the same, what must she make on the 5th test in order to make a B? Now, we know a B is between an 80 and a 90, but not equal to a 90, because if you get a 90, you technically make an A. But you can be equal to an 80. If you're equal to an 80, you make a B. So we're going to bound her grades here between 80 and 90, where it's equal to 80 but not equal to 90. And we're going to add her grades up, the ones that she's made already, the 90, the 88, the 93, and the 85, plus the additional 5th test that she needs to take, and divide that by 5 and put that between that 80 and that 90. Now, if we go ahead and kind of simplify this and solve for x, we'll know what she needs to make on her next test in order to make that B. The first thing I'm going to do is add up 90, 88, 93, and 85, and that'll give me 356. So just doing a little simplification here. Alright, the next thing I'm going to need to do is I'm going to need to get rid of this 5 in the denominator. And in order to do this, I need to multiply this middle term by 5. But if I multiply that middle term by 5, I also have to multiply this term by 5 and this term by 5. So essentially what you'll find with double inequalities is what you do to one thing, you have to do to all 3. Okay, that's your big secret. Now what this will do is we'll get 80 times 5 is 400 is less than or equal to 356 plus x is less than, now 90 times 5 is 450. Okay, so what we will do now to get x by itself is we will subtract 356. But not only do we have to subtract from the middle, we have to subtract from the right hand side and the left hand side. What you do to one, you have to do to all 3. Now 400 minus 356 gives us a 44. This one canceled out, so we're just left with an x. And 450 minus 356 gives us a 94. So as long as she makes at least a 44 and on up to a 94, she's going to make a B in the course. Now if she makes a 94 or higher, obviously she makes an A. And I'm sure she wouldn't complain about that. If we want to write this in interval notation, we're going to put a bracket on that 44 because it can be equal to 44. And we're going to put a comma. We're going to use 94 here. We're going to put a parentheses on it because if it's equal to 94, she doesn't make a B, she makes an A. Very important to write that interval notation correctly. Now we've got another example here. It says 120 is less than 20x minus 40 is less than or equal to 160. So let's solve this one for x. So first thing I'm going to do is I'm going to add 40 to all 3 sides. What that's going to do is going to cancel it out here. 120 plus 40 is 160. Is less than 20x. Is less than or equal to 200. Now I'm going to divide by 20. I've got to do that to all three parts as well. Cancels this one out. Let's see, 160 divided by 20 is 8. So 8 is less than x is less than or equal to 10. Now we need to write this in interval notation as well. We'll write parentheses 8, comma, 10, bracket. And that was example 1. Example 2 says 3x plus 1 is less than 7 and 2x minus 5 is greater than 6. Let's solve these both individually and figure out exactly what this and statement means here. So I'm going to start with this one. I'm going to start by subtracting 1. That's going to leave me with 3x is less than 6. I'm going to divide by 3. And that gives me that x is less than 2. Now I'm going to do this one. I'm going to add 5. Now, this gives me 2x is greater than 11. And I'm going to divide by 2 here. And that's going to give me that x is greater than 11 over 2. Okay. Now, this is an and statement, which means both of these have to be true at the same time. I did a pretty bad job of circling there, so let me try that one more time. But both of these have to be true at the same time. That's what it means when you have an and statement. Okay. Now, I'm going to draw a number line out here to the right, and we're going to determine whether or not both of these can be true at the same time. So, I'm going to go -1, 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now, I'm going to graph this first one here in red. Okay. So x is strictly less than 2. I'm going to put an open circle and draw an arrow that way. The second one here, I'm going to draw it in green. So x is greater than 11 over 2. Now, 11 over 2 is the same thing as 5.5. If that helps some people, you can use your calculator to figure that out. So 5.5 is about right here. It is equal to, so I'm going to put a solid dot, and x is greater than that. Now, let me ask you something. Can both of these be true at the same time? Can we fulfill that and statement here? Is there anything that happens at the same time between the red and the green? No. So, because there's nothing that happens at the same time between this red and this green, they don't exist at the same time. You can't be both less than 2 but greater than 11 over 2 at the same time because of this and statement. Then what we need to put here is that we have no solution. Okay, a little different. Now, this next one, example 3, is an or statement. Or statements are a little different, and I'll show you how that works. Let's solve them first to start with. I'm going to add 2 here, and it's going to give me that 6x is less than or equal to -3. I'm going to divide by 6. And it's going to give me that x is less than or equal to -1/2 if I reduce it. Now we're going to solve this one as well. We're going to subtract 4. And I'm going to get 3x is greater than 5. Okay, so 3x is greater than 5. I'm going to divide by 3. Okay, and I'm going to get that x is greater than 5 over 3. So if I draw a number line for this one, so let's go -2, -1, 0, 1, 2, 3, 4, 5. I'm going to scroll down slightly. And I'll do the first one over here in orange. Okay, so x is less than or equal to -1/2. Well, -1/2 is about right here. It is equal to, so I'm going to do a solid dot. And it's less than or equal to, so it goes this way. Now, here, I'll graph this one in a different color. We'll do green on this one, kind of similar to what we did on the first one. Now here, I've got x is greater than 5 over 3. Now 5 over 3, it's not quite 2, but it's definitely not It's definitely bigger than 1, so it lies about right here. You can find it on your calculator if you want to. It is an open circle because it's not equal to, and x is greater than this. Okay. Now this is an OR statement, and what that OR statement means is that it could be either or. It doesn't have to be both. An AND statement means it has to be both at the same time. An OR statement means it's okay if it's just greater or less than -1/2, and it's okay if it's just greater than 5/3. So it only has to be one. It doesn't have to be both at the same time. So we're going to have solutions here. And the way to write the solution set for this one is what we're going to want to do is we're going to want to say negative infinity to -1/2 with a bracket unioned with parentheses, because it's not equal to here, 5/3, comma, infinity. That lets us know that anything in that solution set is acceptable. And that's how we would write that, mainly because of that OR statement. All right, we got another AND statement here, so let's see how this one works out. I'm going to solve for each. So I'm going to add 8 here and add 8 here. I'm going to get 16x is greater than 20. I'm going to divide by 16. And I'm going to reduce 20 over 16 to 5/4. So here's one of my solutions here. Now I'm going to add 8 here, and I'm going to add 8 here, and I'm going to get 16x is less than 40. I'm going to divide by 16 here, divide by 16 here, and I see that x is less than, let's see, 40 over 16. Let's see, if I divide 40 by 4, it gives me a 10. If I divide 16 by 4, it gives me a 4. 10 over 4 reduces to, I believe, 5/2. So you can check this reduction for me if you would like. I do believe it is correct. 8 goes into 45 times, 8 goes into 16 2 times. This is an AND statement, so we need both of these to be true at the same time. I'm going to draw my number line here. I'm going to go -1, 0, 1, 2, 3, 4. Okay. I am going to graph this one first. X is greater than 5/4. Now 5/4 is like 1 1/4. So it's about right here. It's an open circle. And x needs to be greater than that. Okay. And x needs to be less than 5/2. So we'll do 5/2 in green. Now 5/2, that's the same thing as 2 1/2. 2 1/2 is right here. It's not an equal to, so we'll draw an open circle, and it needs to be less than this. Now this is an AND statement, which means they both have to be true at the same time. And there's only a small area of this graph where they truly are both true at the same time. That's somewhere between here and here, that they are true all at the same time. Both at the same time. Okay, so our true statements are only going to lie between those 2 points. So the way we would write the interval notation for this one is parentheses 5/4, comma, 5/2, parentheses, because it's not equal to both. But the solution set that only works here because an AND statement means they both have to be true at the same time is between 5/4 and 5/2. Anywhere greater than that is only true for one, and it has to be true for both. Any less than that is only true for one, it has to be true for both. So it only lives in this in-between area where they both happen. AND statement. Let's scroll down to example 5, give that one a shot. Alright, now with this one, you have a double inequality. So I'm going to add 5, but I've got to do it to all 3 parts. Now 17 plus 5 is going to give you a 22, which is less than or equal to -3x, which is less than 36. Okay? So that's easy enough. Now I'm going to divide by -3 on all 3 parts. And this division by -3 should trigger something in your mind and say, oh no, if I divide by a negative, I remember that I'm supposed to flip my signs. Gotta remember, with inequalities, if if you divide or multiply by a negative, you flip your signs. Addition and subtraction don't matter, but if you divide or multiply by a negative, you have to flip your signs. Very important to remember that. Now, what that does for us is that changes it to 22 over negative 3 is greater than or equal to x is greater than. Now, 36 divided by negative 3, you should be able to simplify that into a negative 12. Okay. Now, what we're going to want to do is we're going to want to check this on the number line as well, or at least kind of have an idea of it. Now, if you take your calculator and you do 22 divided by 3, or negative 3, you're going to get negative 7.33. And a lot of times that's easier for people to see than just the fraction. But what you want to see here is that x can actually exist between these numbers, because sometimes it can't. Sometimes with that flip, or sometimes just the way the function is set up, or the inequality is set up, it won't actually exist between these numbers and you'll have no solution. But if I'm thinking about it, can x be less than negative 7.33 while also being greater than negative 12? It can. Okay. So if you're thinking about your number line here, so you got a negative 12 here, you got, so we go by 2, so negative 10, negative 8, negative 6, negative 4, negative 2, 0, that is a negative there, make it look a little prettier for you. So we want x to essentially be greater than this negative 12, but also be less than 7.33, which is probably somewhere around here, and it's equal to. So that's perfectly fine. We've got some existence right there where everything is going to be okay with the x. So the way I would put this one in interval notation would be parentheses 12, comma, negative, I'm going to write it as the fraction here, just to be precise, negative 22 over 3, and make sure you put a bracket on that. Always want your smallest one first. If you put your smallest one second, you will probably get it wrong on my math plan. Now let's look at some word problems here. Example 6 says Deb Cook is given the choice of two positions, one paying $3,100 per month and the other paying $2,000 per month, plus a 5% commission on all sales made during the month. What amount must she sell in a month for the second position to be more profitable? Now, let's look at each position. So the first one is $3,100 per month, right? Now, we want to look at the second position being more profitable. So this is the first position here. We want the second one to be greater than the first one. Okay. Now, in the second one, she's only paid $2,000 a month, but she gets a 5% commission. Now, when we change that 5% to a decimal, it's 0.05. So she gets 5% of whatever she makes that month. We're going to call that value x. Now we have our equation set up, and we're going to figure out what it takes for her to be more profitable at this second position. So we're going to solve. I'm going to subtract 2,000 here. Okay, so 3,100 minus 2,000 is 1,100, and that is less than 0.05x. Now, to get x by itself, I'm going to divide by 0.05, and that's going to give me that x needs to be greater than 22,000. So in order for that second position to be more profitable, she needs to make at least, or not even at least, she needs to make more than $22,000 in sales. Now, depending on what her position is, that might be a very feasible option, right? Real estate, cars, right? That's one car. All she's got to do is sell one car a month there. She probably makes more than she does at the other job. But there's other positions where $22,000 a month might be very hard to reach. Could be, I don't know, maybe it might be kind of difficult to do phone sales, even that much a month. It could be difficult to do even furniture, depending on the store you work in your location, to sell $22,000 per month, depending on how big your location is and how much foot traffic you have, right? But if it was like a car dealership, I'd probably go with the second position, because if I didn't sell one car a month, I probably wasn't doing my job anyway, right? Anyway, that's beside the point. Just a little exterior thought for you. Now, let's look at example 7. The percent of the U.S. population with internet access can be modeled by y equals 1.36x plus 68.8, with x equal to the number of years after 2000. When does this model indicate that the U.S. population with internet access exceeds 89%? Okay, so we want to know when we exceed 89%. So what I'm going to want to do here is I'm going to want to do 89 is less than 1.36x plus 68.8. I'm going to want to solve for x. Now, some of you are going to be tempted to use an equal sign here. Don't. Use it as an inequality, because if you don't use it as an inequality, you're going to think, okay, if they make X amount, then they're good. That's not necessarily true here, because if we make X amount, we hadn't exceeded it, we just tied it. Let's go on ahead and solve it though. 68.8. All I'm trying to reinforce is use your inequalities when appropriate. So 89 minus 68.8 should give us 20.2. which is less than 1.36x. We're going to divide by 1.36 on both sides. And 20.2 divided by 1.36 is going to give us a value of 14.85. So our x needs to be bigger than that. Okay, so since our x is equal to the number of years after 2000, when does the model indicate the U.S. population with internet access will exceed 89%? Well, it's going to be after year 2014, right? So 2015, 2016, 2017, 2018, on and on and on, is when we will have an internet access that exceeds 89%. Does that make sense? So what you could even say, you could say, if you want to be extremely technical, you could write 2014.85 is less than or equal to x. If you convert it to years after 2000, you'll be fine there. Now, the very last example says the yearly profit from the production and sale of plumber's helpers is P of x equals negative 40,255 plus 9.80x dollars, where x is the number of plumber's helpers produced and sold. What level of production and sales will result in a loss? Okay, so we want to look at a loss here. So our production value here is negative 40,255 plus 9.80x. And if we show a loss, that means that we have made less than $0. $0 is technically a break even, which isn't necessarily a loss. That's why we're strictly less than 0 here. So what we're going to want to do is we're going to want to solve it. So we're going to add 40,255 to both sides. And we're going to get 9.80x is less than 40,255. I'm going to divide by 9.80. Whoop. It's an ugly 8, isn't it? Alright, and that's going to give us that x is less than, do a quick division on my calculator, x is less than 4,107.65. So basically here, if he sells 40 or 4,107 or less of these plumber helpers, he really hasn't made any money, guys. And this is kind of where it goes into your domain when you have to think about it with a word problem as well. So if I were to write this as a technical domain here, think back to chapter 1.1, right? Is it possible for me to sell 0.65 of a product? No, it's not. Okay, so in the technical area where this exists, where he can show a loss, is between, he can't sell any less than 0, so between 0 and 4,107. And the reason I'm putting a bracket on that 4,107 is because if he sells 4,107, he's shown a loss because it's slightly greater than 4,107 where he shows it equal to. At 4,108, he technically makes a small profit. So he's got to sell a lot of these things, guys, in order just to show a profit. And that happens a lot more than you think. Especially when we're talking about business aspects and selling items that are fairly cheap. You know, it probably cost him a good bit to make this stuff. That's probably where that negative 40,255 came from. And in order to recoup all that money that he invested, he's got to sell a lot of product to show a profit, right? He's got to keep the lights on in the building, got to keep his employees employed and paid, right? He's got a lot of expenses there. So he needs to sell more than 4,107 items just to put any money in his pocket. So our domain here, if we listed it out, would be from 0 to 4,107. And if we want to get really technical with it, and we should, right? It's technically 0, 1, 2, 3, on up to 4,107, right? Because we can't sell any portions of this plumber's helper. You either buy the product or you don't buy the product. You can only buy half of it, right? So our domain would be between 0 and 4,107, putting the whole numbers there. Anyway, that's just a little recap of 1.1. Keep that domain on your mind and keep you thinking about the practicalities of the question. If you have any questions at all about Chapter 2.4, please let me know. Please go onto the My Math Lab and try your Chapter 2.4 homework. If you have any questions with that, please don't hesitate to reach out to me. Also, be prepared. Your quiz is coming available very soon for Chapter 2, so be sure to complete that in a timely manner. And because we have just completed all the Chapter 2 stuff and the Chapter 1 stuff as well as done, when you complete your quiz, you need to be sure to prepare for your upcoming Test 1. If you have any questions about any of that, please reach out to me and let me know, and I will be of as great assistance as I can. Thank you for listening in. Good luck on your quiz and your upcoming test, and I will see you back here for Chapter 3.